think a question is stupid, or it could be a stupid question, I will repeat you what a Russian professor once told me. He said, Fabio, there's nothing like stupid question. There's only stupid answer. Okay? So be aware of it. And now about the physics itself. Where is it that I'm connected? Yeah. So one other thing is that yeah, but then we have to swap. Martín, tenemos que cambiar porque se está conectado el tuyo. The splitter. I don't think so. Switcher. Maybe you can ask Umberto or someone in the. Or maybe I can do this. This went, huh? All right. So one other thing that you might have noticed is that we have dark matter in the morning and like in the early morning, and neutrinos in the late morning. That's because we wanted to keep the heavier topic first and the lighter topic second. No, but no, eu só troquei isso. Soltei aí e pus aqui. But more seriously, we know it's gonna be challenging, okay? We know it's a lot of information coming into your mind, but nonetheless, we would kindly ask you to be very present to it. That also goes into the fact that on board this flight, the emergency exits are over there, and no electronic devices are allowed on board, at least not during my classes. If you feel the urge to use an electronic device, you might as well do so outside, okay? You can leave, I take no offense, but if you're here, be here, right? You have been given something that resembles paper. You have been given something that resembles pen or a pencil, and if you will need numbers, I'll be happy to provide them to you, and we'll go along that way if we manage to set this thing up. Do you have any question about myself, the institute, the other professors, before we start? Yes, please. So I work on dark matter, as you might guess from the subject of my classes. I've been working on other subjects in cosmology and mostly astrophysics of high energies. I think it would be clear at some point what I've been doing. I might even make it part of my class, some of the research I've been doing recently. Nonetheless, before we start, I think it would be nice to know what you have been doing, meaning that we have seen that you guys are coming from different backgrounds, and that's very good also because the topics that we're gonna face are actually very diverse. So I would like to know how many of you had a formal course in theoretical physics, that meaning something beyond standard quantum mechanics, basically quantum field theory. That's less than 1/3. Is that correct? Then I would like to know how many of you have had a formal course on cosmology, that meaning Friedman Robertson Walker metric, not hearing the Big Bang theory, right? That's actually less than 1/4. Then I would like to know how many of you had an introduction or were being formally exposed to particle phenomenology. So not quantum field theory, but knowing mesons, protons, neutrons, electrons, neutrinos. 2/3, I would say. All right. And then I would like to know how many of you had a formal introduction to astrophysics, that meaning stellar formation and evolution, physics of the intragalactic medium, interstellar medium, That's again less than 1/4. All right, that's very useful, I think, for all of us, right? I told you about no laptop, I told you about this, so on my notes there's nothing else. Now what we should try to do is to make this work. I don't have a pen drive, but or I can put it there, sure. If I have a pen drive, if I'm given a pen drive, under, oh, that's awesome. Are you putting any strange virus on my? That's good. It's alright, I just want this to start as soon as possible. Okay. No, but okay. Because it says right. Martín, ¿me das este? Right. No, no la veo. All right. It means that we'll start with our computer. All right. So this, if you can fix it while I start the class, otherwise we're going to be very late. So there is one thing about the problem of dark matter that puzzles me every time I touch it, and every time I work in it. So I think the question of why what I'm doing is very pertinent. Dark matter is not a theory, all right? The dark matter problem is something that arises from a host of observations, some of which are given in a specific context, the cosmological context, some of which are not. They're self-standing. Okay? You can take that thing, completely extrapolate from any context beside Newtonian gravity and known astrophysics, but don't put it in any cosmological context, and the problem will arise again. The strength of the problem will change according to the fact that you're just looking at the local observables, like rotation curves, galaxies, or clusters, or whether you put it in a cosmological context. Okay? The point is that the problem always arises. And what is the problem? Okay? The problem, in general, in physics, there is a problem. And this is a methodological advice that I would like to stress on. Whenever you have something that you think you know, a paradigm. In our case, the paradigm is Newtonian gravity, galaxy formation, galaxy creation, actually, standing of the galaxies, without going to cosmology. And the new observations, some new observations of these objects. And then you find a mismatch if you try to interpret whatever you're observing between the two. Okay? In the old paradigm with the new observations. If there is a challenging, to whom? Qual é o endereço? Sorry, guys. Isabela? Você via premo botão. So, in So the dark matter problem arises, as I will show you, because we have a set of observations, of new observations, that cannot be interpreted in the previous framework, the framework of Newtonian gravity or general relativity. And this will define a problem. Okay? And this first class will be entirely devoted to the definition of the problem only and exclusively on observational and empirical basis, given a set of knowledge that is not going to be disputed. The consequences of this, the interpretations of this, or the solutions are different. Now, when people are exposed to the dark matter problem, usually they are exposed already to conclusions on the solution of the problem. And this is something that is extremely specific of the dark matter problem, but typically you're at a stage of your career that will become increasingly present. Every time you will be presented with a problem, somehow it will come in a suggestion of the solution. This is something that is extremely important for this class and this problem in general, but it's a methodological advice that I will ask you and suggest you to keep. Always look at the empirical facts. Okay? Always form your opinion on the facts and then challenge the conclusions. Okay? Right? These may seem completely unrelated to the technical part of today, but it is. Okay? And well, one of my favorite way of phrasing this, I don't know if you've seen this recent Disney movie. Well, it's not so recent because I'm not so young, but a few years ago there was this called Inside Out about these 5 things in the mind of someone, and at some point they're on the train dream and then the boxes get shattered and everything falls together. And say, oh, this is facts and these are opinions. Ah, they got mixed. Oh, that happens all the time, right? So don't mix facts and opinion. Don't mix empirical evidence with possibility of suggestion of the problem, right? I don't know if we are at this, but the scheme of this class is therefore will be, first of all, let's identify the problem. And this, it will be something which I can call the evidence for dark matter, all right? So today we will go through all the astrophysical observations that hint toward the presence of something that we might call dark matter, okay? And that doesn't comply with anything we know about particles. And I will motivate this statement, okay? The second part is, all right, anticipate the conclusions of today. I do introduce this thing that I call dark matter, and without knowing absolutely what it is, only what is not and what I've learned from today, so that it must be there, that there must be a certain amount, and what is not, okay, I will take it, I will put it in a completely agnostic way in a cosmological context without making any assumption on its nature beside what I know from what today, what is not. And I will see if blindly I'm taking what I know, then I forget where it's coming from. I put it in the cosmological context, I make it evolve, I make a scenario with that thing, and I ask myself, does this prediction from this theory with this piece fit with what I see? Okay, so I double test. So if you want, tomorrow we will have a test of the scenario. A consistency test of what I've learned from here, almost detached from the generic scenario. I put it back in and I see if I'm, oh, it's a little small. Right. That's okay. It's okay. And of course, my take on the fact is that that scenario is standing, right? Clearly, I'm anticipating that. What's going to happen on the third day is that at this point, within the cosmological scenario and within the standard model and beyond, but within quantum field theory, we will try to propose, and Farinaldo Queiroz will do that, we will try to propose classes of particles, not specific models, but classes of particles that can comply with all the properties that I'm taking from the evidence that I show you today, right? But before doing that, I first want to check what the problem is, what the properties of the problem is, and whether the solution, the generic solution I'm suggesting for the problem fits. And at that point, I find the technical things, the very things that fit that part, right? And then, once, but no, this is not okay. This is 2. No, just put like this one. Right. Yeah, it's just working. That's all right. Thank you. So here they will go to classes of models. Meaning something that complying with quantum field theory can give me what I need, right? Otherwise, if I just identify the problem, I test it generically, and then I go and look at nothing that I need exists, doesn't work. And in fact, we will find that there are classes of models, classes of particle models that can comply with the needs I need. And on the 4th, we will give some practical examples of some specific candidate. Okay, so some of the words I'm saying in this moment will make more sense at the end of this class. Okay, and then on the 5th, on the last day, I will get back to you and I will try and introduce you something like how, once I've defined some specific candidates, how I can actually look for them and say, look, I've defined a problem, I've tested a scenario, I've suggested a specific solution, I know now that there can be this kind of particle that is the dark matter. How can I look for that specific candidate? So I will be searching for dark matter, but in some particle model specific scenarios. And also, this last class will connect to what you will see the next week, which are some specific experiments to look for some of these models. Okay, so the program has not been thrown away like that. There is a generic trace to all of it. So that's also why we're asking you a lot of attention every day, because it's gonna trade you up in a sort of pedagogical way. Another thing that I should make as a disclaimer is that, so these are some references for today's classes and for the rest of the week. But one disclaimer I should make: most of the slides that you are seeing today and tomorrow, and probably you already noticed the difference in style between this one, is that I stole and collected and recycled classes from a 2-week school on dark matter that we had here 2 years ago. And the persons that I invited to speak at that school were persons from whom I have very great trust, and they gave amazing classes. That's the reason why I'm recycling part of their slides. And actually, you can find the full course on each of the subjects online. I will give you the link for that school, and I'm condensating the information because there was 2 full weeks on what I'm 2 full weeks. Well, yeah, on what I'm condensing in half of this week. Okay, so clearly you can go beyond every detail that I'm giving today. Today I'm not giving many details, and I want tomorrow, but each point you take, you can go and expand and ask me questions. Today I'm giving a general introduction to the problem. So first of all, local, let's start dipping in. How many of you recognize this plot? How many of you have seen this plot already? How many of you can tell me what that plot is? Yes, what is the rotation curve? The edge. So if this is the galaxy, spiral galaxies, disk galaxies. So if I look at it from outside this way, it looks like this. If I look at it from the top, it looks like this. So this is what? At the edge of the galaxy. Okay, so what's on the x-axis? Huh? Distance from where? Good. So this is the x-axis, right? And on the y-axis we have what? What velocity? The stars rotating in the disk. This is something extremely important. The galaxy, the sort of galaxy that I'm looking at, the stars are confined in a disk, which defines a plane. Okay? And I am completely disregarding any sort of motion of this kind or of this kind, and I'm only looking at the motion in the direction of the board inside. So if you want to look at it, this circular velocity, okay? One thing you might notice, so what I have on the y-axis is this. And then the top is the observed one. So you might notice that it grows, it stays constant. But one important thing to notice is that people don't appreciate it. The galaxy is actually rotating at the beginning closer to the center like an onion. You cut an onion rings, and then the different rings are moving at a different speed. That's what that growth is. So it's not up to a certain point, then it stays constant, okay? It's not like an LP. Like a differential, well, you don't even know what an LP is. How old are you? Right? So it's not, well, no, now they're back in fashion. Now they're hip and vintage, right? But it's not like a CD or there is a differential motion, all right? This is something important to think about. The disk of the galaxy is not constant. It doesn't have a constant velocity. It's detached. But still, you can define a general properties of the star, which is by no means guaranteed. I would expect the stars are just moving around, okay? So, there are two things to notice there. First of all, I'm looking at these only in these galaxies. It's true that these galaxies make most of the galaxies I observe, but nonetheless, it's not given. Second, I have to be sure that the stars and the disk are moving coherently. Otherwise, I can't not even define this plot. It doesn't even make sense, let alone what it means. Okay? Right? Now, given that you believe me, and I'm telling you, the stars and the disk basically do not have sizable dispersive motion. Ring by ring, the up and down motion is coherent, or it doesn't add to the noise. The radial motion is also negligible with respect to the problem, and every time I decide a section of the disk, the motion in there is consistent, okay? And it follows the rotation of the. This is something that I invite you to check out. And the stability of the disk is something that has been a problem in galaxy formation and evolution for a while. But if you want, that comes from the fact that there is angular momentum conservation, and when I start from the cloud of gas and stars collapse, they form into a disk, and that disk is stable under rotation. Check it out. But now this brings us to the next property. The disk is stable under rotation. What does it mean? That means that there is a balance between the gravitational force pulling in, okay? So again, this is the disk. At each point, there is a balance between the gravitational force pulling in and the centripetal force pulling out, okay? And this proceeds from what I was saying, that this disk is formed under conservation of the angular momentum. This is non-trivial. To get to this is already a lot of stuff to understand and confirm. Well, now we understand it, but in principle, you should go through all the pain of understanding that from doing the computation of the angular momentum yourself. But this tells you that any of you that is coming fresh from this might recognize that the centripetal force depends on the velocity, right? The radial velocity. So if I'm here, I'm balancing the velocity, radial, because that's what gives the centripetal force. And there I'm balancing what? The question is, I just told you that the disk is stable under rotation, right? So it's rotation supported. So the gravitational force is balanced by the centripetal force. Now, therefore, there is a relationship between the two, right? But what's the physics of each of the two? What's the physical thing that underlies each of the two forces? So in the centripetal case, it's the velocity. I don't know what the nature of this velocity is, but there is a velocity, and that creates a centripetal force. No, at each given radius. I'm sitting here, okay? So this is the center of the galaxy. This is the chosen radius. So at each radius, this thing will be true. And then I have a force, which is generated by the velocity, whatever is the nature of the velocity. Don't care. But so this centripetal force traces the velocity, and this, the gravitational force, traces what? The gravitational field. So the mass where? The mass enclosed in this sphere. Okay? And I was telling you, at each radius, this is true. Okay? So this is historical part. We can get to that later on. Okay? But so I know that at each radius in the galaxy, the centripetal force that I can write as the mass of the element, v square over that given radius, is proportional to the enclosed mass at that radius. Okay? Yes, there is a mass here, right? So they go away. Thank you. So it doesn't matter what the mass element is because the force acts on the two, right? So what I'm trying to show you here is that this is generic at each point, but the point that I'm trying to make is that this is a dynamical quantity because the mass enclosed is the mass of the stars or whatever is in there, and this is dynamical. So if I go back to this plot that I'm showing you, the data, what I'm seeing on the data on the top is the rotation velocity as a function of the radius that I can integrate out into a mass as a function of the radius. Okay? So I want you to point on the fact that this is not an opinion. This is a fact. If I believe that the disk, and again I told you there's a framework out of which this arises, and the framework is not cosmological. I just believe, for good reasons that we can elaborate upon, that a disk galaxy has a disk which is rotation supported. If I believe that, and I believe that for good reasons, by observing the rotation velocity as a function of the radius, I have access to the mass enclosed. Okay? Period. That's a fact. So, given that, the one on the top, which are the data, I can extract the mass profile. This was going to be one of the exercises because you just have to integrate this out. Okay? You had a question. Yeah. It's a fantastic. It's spherical. It's spherical in 2 dimensions, but it's spherical. It's spherical in 2 dimensions, but it's a sphere. If you apply correctly the Gauss theorem, you will find that this statement is correct. That's a very good observation. Practically, you can integrate it out. Very good. No, it's a very good observation, but it's true. Okay. Any other question? Yes. Todavía no hemos hablado de discrepancia. So he's asking about the discrepancy between the observed rotation curve and the one predicted. I still haven't touched the predicted. Let me get to that, okay? Very good. So again, this is an example of why I'm trying to fix the facts, because otherwise we start looping around. I know it's taking a bit, but I just want to, one thing is the observation, one thing is what I know, and I want to get to that, okay? So right now, from the rotation curve, so I will call it RC, rotation curve. From the rotation curve, it's an observations. I go to the observed enclosed mass as a function of the radius. Do we agree on that? That it's an observation. It's an empirical observation. Well, the velocity is an observation. Technically speaking, no. Actually, the photons are an observation. We observe the photons. We don't even observe the velocity. We take it from spectral distortion or redshift. So I infer an observed mass, enclosed mass at each radius. All right? I want to see it in the space of velocities because it's most convenient, but I can trade one for the other. Okay. Now you see, and you obviously know, this falling curve on the underneath. that I don't want to show you at this point. Actually, it's better to see this one. Where does that curve come from? This is the prediction you're talking about. Okay. Now my problem is, okay, I already know where to look for because this is the dark matter class and we all know the problem. But the thing that I want to check is now, is there a problem? Where does the problem come from? The problem comes from the fact that I know how many stars there are in the disk. Again, you should believe that I know how to integrate the spectra, the luminosity that I observe from the disk. I integrate it back to the mass of the star because I know each star, what spectrum does it have. That relates to the mass of the star, right, Andressa? We know that the spectrum traces back to the mass. So again, I'm in a framework where I know things. It's an astrophysical framework, but it's a solid one. But based on that, I can tell you what the mass of the star in the center of the galaxy, meaning the central region, and the disk is. Okay? So from one set of observations, which are mostly spectral observations, not kinematical. So again, you might appreciate that one thing is doing kinematical measurements of velocity, the other is to make spectral measurements to get the star, the mass of the stars. So here, from that, I can infer a stellar mass. Okay, and actually I don't even infer it as a function of the radius. I infer it as a function of whatever it is, so as a map of the sky. But it's convenient to write it down as a mass as a function of the radius. Okay, so again, there is a new set of observations, spectral, that tells me the mass of the stars. Right? And from that, I adopt the Newtonian framework that I know to be working. You can actually also adopt a general relativity framework. That's not the case because the acceleration regime is not the one that gives you general relativity effects. But if you want to be picky, you can do it. Right? You're just wasting much more time. Actually, this is going to be an exercise. You're going to compute the acceleration scale and make sure, and the velocity scale, and make sure that this is not belonging of the general relativity. Useful exercise if you want. I'm going to give you numbers and then you can do it on your own. But again, Newton is fine here. So I take again the Newtonian framework, and from that, since I have a set of observations which are the radial velocity, the observed radial velocities, I want to compare with that observable because it's convenient. So from that, I just adopt the, if you want, predicted rotation velocity starting from that observation. Okay? And that's nothing else that gm star that I have observed somehow divided by r square. This is square. Okay? So this is your question. This is the thing that you were using, right? So this curve that you see underneath is this one. Okay? Now, you can believe what I'm saying, right? That curve is that, but one thing that you might notice is that that extends up to 20 kiloparsecs. So now I'm just trying to give you some feel of the scales, okay? I can observe rotation velocities up to very far out, say 20 kiloparsec or 30 kiloparsec, in some cases up to 50 kiloparsec. Okay? What's the size of our galaxy? Why is that much far out? Our galaxy, or M31 Andromeda. No, our galaxy is 10. The disk extends up to 10 kiloparsec. Okay? Everything what? That's the radius of the disk is approximately 10 kiloparsec. We're sitting here at approximately 8. Okay? We live in the outskirts. It's called gentrifications. We were sitting in the bulge, but then they kicked us out and all the families are moving in the outskirts. So, but the point I'm trying to make with this, even if you don't know the detailed distribution of stars, you know that the entire mass of the stars is concentrated within 10 kiloparsec, okay? So if you want to be crude, like really beastie, you say that outside 10 kiloparsec, you just go like gm over r, okay? The velocity must go like gm over r, okay? Is that correct? Because I'm just skipping all the details. That's the mass enclosed and it doesn't change because there's no more mass. So wherever I observe something outside, and again, you should be asking, if there are no stars, if I'm observing outside the disk, where I'm taking these stars from, because there is no disk anymore. And the truth is that I can use gas clouds, but they do the same job, okay? The thing is that that should go like 1 over the square of the radius, okay? Like square root of the radius. So I do expect whatever the details of the distribution are in the disk, and I can get the details. But again, if I want to be crude and simple-minded, I look at stuff outside of the disk, and I do expect that if this is the velocity and this is the mass, okay? So I have a mass that goes like this. The mass goes something like this, and then it stays constant, okay? Right? This is where the disk is. So I do expect the rotation velocity to do something like this. If I go Newton, I do expect something like this, grow and then go down like 1 over the square root of the radius. Instead, what have been persistently observed is this, okay? Which you're seeing on the top, and that Vera Rubin was observing in a lot of galaxies. Okay, you might notice that that extends 5, 10, 15, 20, 25 kiloparsec. There is no galaxy with such an extended disk. Okay, typically you can't go beyond 15 kiloparsec, the disk of the. So I am not still addressing what's the discrepancy, but now I know for sure that there is a discrepancy. Okay, and we've done the math a little bit, and we're based on interpretation of given data. I am not taking any framework, specific framework, just a little bit of astrophysics, which is what I need to know to interpret these observations. But I know that there is a strong discrepancy. I don't know how to modify that. Either there is a mass enclosed that I'm not seeing from the stars, that's one possible explanation, or either I have to modify gravity. At this stage, I can't say anything else, right? Good. So let's say that from the rotation curves, I have an observed mass, and then again, so these are observations. And then from spectral, I have a determination of the stellar mass that goes into Newton. Through Newton, I go to a predicted from the stars rotation curve. And this one is actually not the same of the observed rotation curve. Okay? And this is on the scale of 10 to 20 kiloparsec. Okay? Not addressing any nature of this discrepancy. I'm just observing it. Okay? Good. Yes. Mm-hmm. The one that I just erased. Yes. Oh, that's true outside, as I was saying. Close to the origin, you have no mass. That's true outside of the disk. No, actually, it's not even m star. The velocity is proportional to what? To the square root of m over r. Is that correct? But now m is not fixed m. M is equal to the integral of rho dv. Okay? I cut this plot where I knew that all the mass was enclosed. So outside the disk, this goes, m is given, this integral is a finite number and it doesn't change because all the mass is enclosed within the disk. So outside here goes like this. Inside here it doesn't go like this. obviously, because I have to integrate a density which is a function of the radius. Okay? Exactly. But even to define the total amount of mass here, I need the observations. We do this self-consistently. Now I'm giving you a simplified example to show you that there is a discrepancy. Okay? Actually, I have an exercise on this where you can also notice a little bit of things. If you look at this plot, and I'm not giving you many more elements, but this is important, mark it in your mind for what's going on tomorrow. You will notice that the discrepancy between the two, okay, look at that long dashed line, okay? Or where is most of the discrepancy coming from? Give me a number, please. That the tickles on the x-axis are kiloparsec. Where you would say, if you look at that plot, that there starts being a discrepancy. 4 or 5, but not the center. Right? This is extremely important. Extremely for the consistency of the scenario. It looks like a detail, but fix your mind on it. Okay? Okay, so we defined the problem. This was a slide that Pasquale put together. And so you can see again, on the top plot on the right, what is devising is you have the data on the top, then you have the raising and decreasing curve. And then, again, this is going to be an exercise. But he's saying, look, if I want to fix the problem with an additional mass, as we said, we have a problem, then there are two ways to fix it. It's clearly related to gravity. So there's two ways to fix it. Either I put more mass or either I modified gravity. In this moment, I'm choosing to modify the mass. I'm just saying, look, there is some mass that I'm not seeing for some reason, but it's matter because it generates gravity, and it's dark because I'm not seeing it. And what do I need to fix that thing? Something that grows as a power law in V. Okay, it's just an exercise. I'm just saying, what do I need? And again, this goes in the direction that goes to 0 in the center because the discrepancy starts around 4 or 5. In the center, you have virtually no discrepancy. Again, well, let your minds dwell on it. Okay, enough for spiral galaxies. We've been close enough to the center of the problem. And let's go to something bigger, which actually historically was the first suggested observation of dark matter. Okay? Completely different system, a galaxy cluster. Do you know what a galaxy cluster is? There are very few things that are well posed in physics in terms of terminology. One of them is dark matter, because it's dark and it's matter, and the other is galaxy cluster, because it's a cluster of galaxies. All the rest sometimes doesn't make sense, but a galaxy cluster does make sense. Well, obviously, there's more to it. A galaxy cluster is something that I have to know. There is a cluster of galaxies clustering together, but I have to know that they make an item, okay? It's not just galaxies that happen to be in the same field of view, okay? I have to know there is a bound system. Otherwise, it's like you go out in the street, you see a lot of people walk and say, hey, this is a group of people, they're having fun together. No, they're just crossing their paths randomly. There is no force putting them together. So, of course, I have to make sure that the people I'm seeing or the galaxies I'm seeing are bound together by something. Maybe there's a desk with food and drinks. That's the uniting force. And in the galaxy clusters, these galaxies actually have a random motion, a seemingly random motion, but I can tell that they're bound to each other. Okay, so this is extremely complicated to do it. Actually, I think defining a bound system in clusters is non-trivial. But again, let's sit in a framework in which I know the astrophysics of the system. Again, I'm throwing things that you should be asking me, right? How do I know that a cluster is something? But let us say that I know that there is a certain volume where galaxies are. Okay, right? Again, this is not what I see. What I see is just galaxies in random motions around. This is what I see when I say galaxy cluster. Okay, And what I see is that I see individual galaxies that at the time were called nebulas, okay, moving in certain directions. How do I know that? Is because if I look at the nebula, there is a shift, a radial shift in the spectrum, so I can tell what the velocity is, blue shifted or red shifted. Of course, I'm choosing the first cluster in such a way that there is no cosmological redshift, it's just a local redshift, so there is no Hubble flow around me, and I know that these objects are close. And what I do is, for some reasons that I'm not giving now, because we're actually really running out of time, but for some reasons, I know that I can consider this as a bound system, okay? That means that nothing is going out of the system, it's a conservative system, okay? And there is a motion of the things within the system. So what I can do is define what is called the Virial Theorem, which is a theorem that I can define at a higher order in phase space with a conserved function, but for practical purposes of this system, is just telling me if I look at these as a gas in a gravitational potential, a collisionless gas in a gravitational potential, the kinetic energy must be of the same order. Actually, there is a half somewhere, but say it's order 1 of the potential energy. Okay, that's it. We can go to a more refined way to do that. But basically, it's telling me the temperature is proportional to the total mass. Okay? This is it. And this is what it was done. Now, the problem is, again, look at what I observe on one hand and what I observe on the other, and is there a mismatch? Okay? So I have it. If I want there to be a problem, or if I'm setting my mind to find the same problem that I found in galaxies, I have to say, I have to get the total mass from the observation of the potential, okay? And I have to take the kinetic energy that I take from the motion of the galaxy and see if there is a mismatch from the two when, once I observe, so what I'm doing is I'm observing the motion of the galaxies, and I know that the Virial theorem applies, okay? I'm observing this. From that, I estimate the total potential, okay? And then I say, okay, I see galaxies. The potential must be given by the mass of the galaxies. I take the mass of the galaxies. I compare them with the mass that I've obtained from the Virial theorem that I obtained through the velocity of the galaxies. And, oh, there is a discrepancy. This is what Zwicky did, okay? Now there are more refined ways to do it. But historically, so the path is, there is a bound object, and then I have the Virial theorem applies, this is the logic axis. And that means that I can relate kinetic temperature, that means velocity of the galaxies, to total mass, right? There's a proportionality between the two. These I observe, and so through the Virial theorem, I go to an inferred total observed mass, okay? At this point, I take another set of observations, which is the integrated spectrum of the galaxies, okay? So I take another set of observation, spectral. I sum them up, okay? And I take a mass of the galaxy estimated through the luminosity. And ta-da, these things are not the same. Again. And the discrepancies of the same order that I get if I take the mass of the galaxy at 20 kiloparsec. There is one major problem. This scale is 1 megaparsec. So the size is 100 times bigger. The volume is therefore 10 to the 6 times bigger. The acceleration scale is ludicrously the same, because the mass of the cluster is different. I have very remarkably little time at this point. Half an hour, no more. So, again, this is puzzling because I'm in a completely different type of system, right? The galaxy was a disk of stars supported by rotation. Here I have something that I basically have defined as a gas. And the individual objects of this thing are of the mass of the integrated thing of the other system. And the physical scale is much bigger. The spatial scale is enormously bigger. Okay? But again, I'm identifying the same problem. Okay? So, can I fix these two problems at the same time? Add more matter or modify gravity? We still don't know it. And I don't want to suggest any solution. But there is one problem though. I told you that I compared the luminous gas, the luminous matter, with that of the galaxy. And I know today that actually the mass of the galaxies in a cluster is negligible with respect to the mass of something that is luminous, just not in the optical, the gas. Okay? I know that most of the mass in a cluster today is in gas, intracluster gas. Well, galaxies are made of gas because they're made of stars, and the stars are made of gas, but diffuse gas, okay? And how to observe this in X-rays? Okay? How do I produce X-rays with gas? I didn't hear any of you, whomever was. Huh? So it must be ionized. So it's ionized gas. So from knowing the temperature of the gas, I also know the mass of the cluster. So the X-rays are a way to weigh both the fact that there is gas and, on the other hand, to weigh the total mass, because the total mass is dictating, if I assume hydrodynamic equilibrium, the temperature of the gas. Okay? So for free, I'm getting another method to estimate the total observed mass. Okay? And actually, I can even trace the profile of the total mass. Exactly like in the, well, exactly, it's not exactly, but similarly to what with the galaxy, I could trace the evolution of the enclosed mass with the radius. With this, I can actually trace the mass of the enclosed gas. And again, this is going to be important. Okay? But let me mention one thing. Again, this method has to rely on the assumption that there is an equilibrium between pressure and gas. And I don't want to do it for the moment. And again, when I estimated the total mass, I adopted the Virial Theorem. The Virial Theorem holds under specific conditions. This should be a collisionless gas, okay, as I said. And we can convince ourselves that it basically is. Actually, I'm going to give you an exercise on that, because I want you to get your hands dirty with the numbers. You have to feel the numbers. But there is something that is, I'll go very quickly on that, but it's actually related to your question, right? Your question is, when I ham in the disk of the galaxy, now I'm going back to the galaxy, but all these things are related, how do I know that there is no contribution from the outer parts? Well, first of all, you can integrate the Gauss theorem 2-dimension, and you can convince yourself of that. But on the other hand, now let me pause here, because I gave you enough information. Sorry. Let me make a small recap, okay? Just a second. Let me rewind back a little bit. You know what rewinding is? No, because you're young, you didn't know what tapes are, right? So I identified the problem in the case of the galaxy, and I identified the same problem, if you believe the Virial theorem and the spectral integration of the masses, at the scale of the cluster. But remember, this is a scale of tens of kiloparsec. This is a scale of megaparsec. Also, the mass involved here are something around 10 to the 11 solar masses. The masses involved here are 10 to the 13, 10 to the 14 solar masses. Okay? So we're talking 2-3 orders of magnitude difference in terms of the mass. Of course, the distance is different, so when I compute the acceleration, maybe these things don't get too far away, but again, of course, there's much more details that you have to work out. But I want you to convince yourself that it seems like the problem is similar, but I'm in completely different systems. okay? With completely different astrophysics also. Like in this case, I'm using kinematic observations of stars in a disk, and I have to make a certain set of assumptions. Here I'm observing spectral motion of individual galaxies and making another set of assumptions. So again, I might be failing somewhere, but reasonably is not the same mistake, and I'm getting exactly the same result. Okay? Recap that. On the other hand, if I want to get rid of some of the mistakes that I might be doing, rather than believing the disk approximation, I could just do a Jeans analysis. Once I convince myself that either the cluster is a collisionless system, so the individual galaxies act like particles in a gas, or either in a single galaxy, stars act like particles in a gas because the interaction between individual stars is negligible, and that I can do very well and very quickly. Okay, you can do it, you will do it. Then I just take Maxwell-Boltzmann, a perfect gas with potential, and I solve the phase space distribution. That's a purely formal way to do it. Okay, and at that point, I'm sensible. I can take observables all over. And that's actually what I do with some galaxies. I don't want to get into so many details, but again, because otherwise we get stuck. But I want you to get exposed to the fact that for a galaxy, especially for small galaxies where a disk doesn't even exist, a small galaxy, like a dwarf, it resembles a little bit like a cluster. So it's an ensemble of stars that are basically pressure supported, okay, by the pressure of the gravitational potential. I observe these stars. I take the Jeans equations that it's basically is giving me different terms. So I have the velocity divergence, you have the evolution of the phase space, and you have it's related to the potential there. But one important thing is that the integral of the phase space distribution in the velocity tree space gives me the particle density. Okay, so I basically, once I solve these equations from some observations that I have to relate, I can get the density of the particles, and that tells you the total density of the particle, the total mass. And because I'm just looking at the motion, more formally, I obtain the same answer. And there is actually a remarkable case that is not this one. This is, I'm writing the Jeans equations for a specific case. I can even solve the Jeans equations for a specific case, which is the disk of the galaxy. Then I zoom in and I obtain this section of the disk here, and then I look at the motion of stars up and down the disk. Okay, and I can solve the Jeans equation for this small slab. Okay, and I find that even in this small slab around the sun of 100 parsec, if I take the density of stars that I do observe and I take the motion up and down, I still am missing matter on the scale of 100 parsec. And this you can do with a simple exercise I can give you. So you integrate the Jeans equation for a specific system. Okay, you take the observations, which is the velocity of the stars, and then you take the density of stars observed, and it doesn't match with the density of matter that you retrieve from solving this equation. Okay, so again, your logic might be failing at some point, but it can't be failing in all the points. And of course, everything I'm saying is much more detailed than this. This is a reduction class out of 5. You should really go to galactic dynamics to understand the problem better. But what I'm giving you here is a flavor of all the things that I can do on all the scales, and the problem always presents itself. Okay, always. Let me go also to another important point. I told you that in order to obtain, again, so I went back to the galaxies, now I'm going back to the cluster. So I can use the Virial Theorem to infer the mass of the cluster. But today, we have weak lensing, we have strong lensing, we have gravitational lensing. Okay. So I don't know how many of you are familiar with lensing. How many of you are familiar with gravitational lensing? Very little. So I will not go through the details of this because there is no way I'm going to condensate this to you. But obviously, the game is that I am here, I'm observing, then I have something that acts as a lens. Then I have an extended source, and I'm supposed to be seeing this here. So this is the apparent position, okay? Then there's also a lot of rays that go here, and then it looks to me that this thing here, okay? So I'm seeing a distortion. It's just all there is to the lens. Now the point is that there's very different types of lenses, okay? So there is cases in which the lens is really within the lens, so the source and the lens, so the whole source is within the lens. Now, in our case, the lens is a mass. And this equation that you do in optics, I don't know in Brazil, when do you do it? Took my undergraduates, you do it in the second year. I've long forgotten it because it's been a very long time ago. But the whole point is that the lens is the mass. And the form of the lens is given to me by general relativity, and I can easily compute this for any form, not easily, but I can compute this for any form of the mass. So whenever I want to use lens, whenever I want to estimate a mass, the best way to do it is today to use. Of course, you have to reconvolve the distortion of the individual lens, of the individual sources, distorted sources or super sources, into what the mass of the lens is. But this is a complicated business, but there's a lot of people working on it. So especially for clusters, this is actually quite easy. Let me skip this, because when I go to clusters, there are sizable distortions, okay? So there's different types of lensing that are important to us for the clusters. That's strong lensing, okay, when you create either multiple images or heavily distorted images, so you create arcs, you create multiple images of the galaxies. For the reconstruction of the mass in a cluster, weak lensing is better because, or some, but again, if I use the two, I get basically the same mass estimate that I get from the Virial. They're in amazing agreement, and that I get also from a Jeans analysis, which after all is the Virial Theorem in it. Okay, so again, today what I showed you is a very introductory way about how things were done in the 30s and historically, but today I get very good information about the total mass of the cluster from lensing as well. And lensing is extremely useful for another reason. Okay, now let me reset. We have the evidence. Do you believe what I showed you? Is it reasonable? Can you find any dramatic logical fallacy in either the galaxies or the cluster? I would like at least one of you. Yes, you can. How's this done? Tá funcionando.
Então, eu não sei como que é feito esses cálculos de massa luminosa, mas como que você pode fazer isso e ter tanta certeza? Qual que é o nível de certeza que você tem nesse cálculo de massa luminosa que você fez? Tá certo que você falou que depois você consegue obter os mesmos resultados por lente, né? Mas...
So the question is, how can I be sure of the luminous mass? Well, first thing, and how does this compare to the lensing mass?
And another mass used to made by
okay,
Virial
so
Theorem.
First of all, conceptually, the mass obtained through lensing, okay, conceptually, that compares to the mass obtained through the Virial theorem, right? Conceptually, because it's the total mass. And then I compare it to the luminous mass inferred by the spectral thing. So how do I get this? Well, I have to how do I get what are the observations that lead to estimating the lens, the mass through the lensing? It's the distortions. Well, You would have to go through how you build the lens model from general relativity, but the basic observation is the distortion. If you want the observational uncertainty is on the distortion of the galaxy. Now you might be even asking, well, if I am observing a distortion, I must know what the original shape is. Otherwise, it's not distorted. It's just an image. I don't know what the original is. So of course, there is many more details. So that's a very good question because it shows you how many layers there are to the problem. Okay, but the thing is that I am not an expert on general relativity, meaning I don't do this, but there is a way to estimate what's the original image, what's the distorted image. Then you have different parts of the tensor because the distortion can be linear or there can be a shear in the distortion. And that uncertainty also, of course, you will have associated uncertainty to that estimate. Those uncertainties propagate through the lens model, and eventually those uncertainties will give you this, okay? Then here I observe individual motions of galaxies. So that's sort of easier because I just have an uncertainty on the spectrum, but still I will have a plus or minus delta m vt, okay? And if I compare these two, so m plus or minus, they are compatible, okay? Here I will have a plus or minus delta m comes from the spectral integration of the luminosity of each individual galaxy, okay? There is a shape to the spectrum. That spectrum tells you how many stars there are and what types of stars, so you can weight it. You know the mass of the stars inside. And of course, you will have this. If you compare, now we said these two are compatible, so I take one of the two. I compare it to these, and they're not compatible by a factor 5. Okay. How I can convince myself that each one of these is true. I have to go through the details of the method and develop gravitational lensing part and know what I'm doing every time I build a lens model. I know I'm making sure that there is a shear distortion. I cross-test it with all the galaxies in the background. I have to make sure that the galaxies are in the background and not in the foreground, etc., and so on and so forth. But the method is amazingly complex. It's a very good question because it shows that you have to have upon the details.
My question is about the luminous mass. How
luminous
you
mass
can be
is this one.
so sure that that's what you see? Is that what you have of mass of?
Because integrated spectra of galaxies are an extremely detailed field. There's people doing it even here in São Paulo at USP. There's a lot of people. So what you do is you take the spectrum of individual stars. You know that if there is a stars with a given metallicity and a given mass, it will have a certain spectrum. You take a galaxy made of a certain amount of stars from theoretical models. You make up the spectrum that it would come from so many stars of a certain metallicity. Of course, you also observe the metallicity, so you have a hint. You put them together. You have the spectral distribution, well, in your reference frame is spectral distribution that you would expect from that type of galaxy. You have a library of that. So you take the observation of the galaxy, you confront it with your library, and to the best of your knowledge, you can say that's the mass of the galaxy. So, a very good question, but this is to show this is not hocus pocus. Every single element of this is going to bring you to an amazingly stratified level of detail. You are seeing approximately 60 years of research on lens together. And I think it's very good that we understand that the evidence for dark matter at this, not dark matter, at this moment we have just the evidence for a mismatch between observations and predictions from other type of observations in a non-cosmological framework. Again, this is completely local. I'm overshooting my time of approximately 100%. I wanted to talk about this 30 minutes ago, but I am happy if you understood the details of this. And I'm happy if you understood that I'm getting this evidence for the discrepancy that I was mentioning at the beginning, but now it's well posed to talk about the discrepancy because you're all convinced of this discrepancy. And it's a multi-approach problem because it comes from a host of different observations in astrophysics. Okay? Now, I have 5 or 10 minutes. Are we convinced now that, of course, if I'm not selling you smoke, this this mismatch is very serious, and it's there. And it's there on objects of different scale, right? Now, as I said, I wanted to get to the problem. There's a problem. It's dark matter. What it is not. I'm not going to be able to do it today. But what is it then, right? I know that there is a mismatch between whatever gravity I'm expecting from luminous mass, from stuff that is luminous, and from the actual things that I observe, from the potential that I observe somehow. It doesn't mean that there is any, well, let's say that we don't trust modification of gravity for a host of reasons. We can talk about it in a discussion session, but for now, let's, I'm not saying it's good to give it for that, but let's assume it's just dark matter. What can it be? It doesn't mean at this stage, it doesn't need to be anything strange, right? It can be planetoids. It can be cold gas that it doesn't shine in the X-rays, right? I have seen that I thought that the masses of the galaxies were not okay. And then I find out that there is gas in the X-rays that makes most of the mass of the galaxies. It still doesn't match with the gravitationally observed mass, but nothing prevents me from thinking that there is some cold gas that I'm not seeing, or some planetoids distributed. And okay, let's get rid of the planetoids, of the machos, okay? And it's massive compact objects, halo objects. Yes, there's an H missing. So again, what prevents me from thinking that if I look at the galaxy, I've said I've taken the mass of the stars from spectral distribution, so I'm looking actually at the luminous mass, but there's planetoids like Jupiter size or sun size, but 0.4 the sun size, or 0.04, and these are stars that are not shining, they're brown dwarfs. Okay, I don't see them, they're in the galaxy. Why can't they be? And there is one simple reason that I can get from gravitational lensing. I'll leave you with that. There are very good reasons why it can't be gas, galaxy, but there are different lensing regimes, as I told you. Okay, and one important thing is that if I'm looking at the lens here, this is the lens, so this is my mass lens, and here is the source. There are different regimes. But one important one is that the strong and weak lensing, I'm creating multiple images or not, but the angular scale is such that I can separate this from this and the sky. Okay? What happens if this scale is so small that I'm creating another image? I'm blind. I cannot distinguish. Well, I'm myopic actually, not blind. I'm presbyc. Or whatever. There is an aberration in which I can resolve only this. So I have these two images together. Okay. I see an alteration of the flux luminosity. Well, I just see an enhanced flux because I have another image on the top. As a matter of fact, if something is passing through the lens field, so here is the lens, is me, and this thing is moving, here I will see, what I'm going to see is this. So here, this is time, this is the intensity of the objects, and let us say that there is also space. Okay, so I am seeing, here is the lens, and the thing is going here, 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 here. So here I am, and I'm seeing lensing effects between here and here, right? And here is too far away, and I don't see lensing effects. What happens to the flux is the flux is constant. I'm monitoring this object. The flux is constant. And then at some point, the images are created because I fall within the Einstein radius and I create the image, but I cannot resolve them. So I see an enhancement of the flux, and it goes back. Okay? This thing is called microlensing, and it's very thoroughly studied. And this is created by small compact objects. The gas cannot do that because the gas is diffuse and it cannot create an image at this level. It can create weak lens. So basically, the point is that I can monitor these objects. Okay? And the proof of principle that is, well, actually is a technical, that it cannot be planetoids is that if I am sitting here, I'm sitting here in the disk of my galaxy, I'm quiet, sitting here, and I'm looking at the Large Magellanic Cloud, or I'm looking at Andromeda. That's off the disk, okay? So I'm looking in that direction, and I can actually monitoring all the microlensing that is going on to the objects there. Now, the M31 has basically the same property of the Milky Way, so I know that if I believe in the dark matter option, there must be a halo of dark matter objects around. Now I'm testing the hypothesis that these dark matter objects are made of planetoids or compact objects. Okay, that means I take the rotation curve of M31, I add the component to the mass component that fits the rotation curve on the top of the stars, and therefore I know that there is a halo of these objects, because in this moment I'm testing this hypothesis. So I have the dark matter halo of the M31, which is made of these objects. Okay, I do, if I believe that they are Jupiter-sized or brown dwarfs, since I'm here, I must be seeing the stars in M31 continuously microlensed by this one. Continuously mean that I take the function that I expect to fit the rotation curve, I assign a certain mass to the object, I make my calculation, I know how many microlensing events I do expect from the stars here, I monitor those stars, and I see none of these effects. Of course, there's also all the objects of the Milky Way, because the Milky Way also has a halo, so I have to integrate the two. This is well done, and I find none of this. Okay, so this is not my favorite argument, but it's one argument, and there's redundant arguments for saying that I believe the clusters, I believe the galaxies on different scales, I know there is a missing component, and it cannot be planetoids. That still leaves open the possibility of cold gas that doesn't make the microlensing, so this argument wouldn't apply. But I leave it for tomorrow, why it can't be. And that at that point, we go into the cosmological framework. It's extremely exciting, I think. But few things that I would like you to take out from this class is there is a mismatch at the scale of galaxies. And I try to convince you that even if you follow the dynamic of the disk, or if you perform a full genes analysis, there is a mismatch between the total enclosed mass at different points, and this is also very important, different stages at different points, between the observed gravitational potential, the observed total mass, and the luminous mass. There is a profound mismatch. Same thing at the cluster scale. There is a mismatch between the observed gravitational mass and the observed stellar or galactic luminous mass. Okay? I use different sets of observations. Then I compared it sometimes in the space of the velocities, sometimes in the space of the masses, but the whole point is that there is a mismatch between the gravitational mass and the luminous mass. In different scales, 10 kiloparsec, 10 to the 10 solar masses, opposed to 1 gigaparsec, 10 to the 13, 10 to the 14. I used weak lensing, I used strong lensing, I used kinematics, I used the Virial Theorem, I used the genes analysis, I used a host of things. Okay? Other thing, I just try to point you to the fact that the most obvious explanation for this mismatch, there is a mass which is not luminous and is nothing very strange at all, just brown dwarf or things that I don't see for good reasons. It can't be. Not in the galaxy, it can also not be in clusters, because you cannot form these things in the intracluster medium. Right? And I know this with a high degree of precision, because microlensing is a very good technique, weak lensing is a very good technique. Okay? It took a little bit of time, but I want you to get the methodology right. I don't want anybody to be mixing facts and opinions 3 days from now. Very important for me. Okay? I think I'm late of 5 minutes, but that was your fault. It's true. Not for long. Okay, so I think I'll take 2 brief questions right now, no more than 2, from 2 different people, not from the same one, and then we go for breakfast. You wanna give him a microphone, because I think all this is getting recorded.
Hello. So my question is, throughout the explanation, you mentioned that it could be that we're having more mass, or we just have modified gravity, right?
I didn't say just, or you have to modify gravity.
Yeah, but let's assume those 2 options. So my question is, throughout the explanation, we are ruling out modified gravity as an option because we're focusing on dark matter. But my question is, was there any fundamental experiment that allowed us to rule out modified gravity and therefore search for dark matter?
Yes, but I didn't mention it. What I did mention is that at the moment I'm concentrating on the mass option. We can talk about modifying gravity later on, but if you want, the fundamental reason is that we perfectly know general relativity, and there is no... So what I'm going to try to do tomorrow is to show that a generic cosmological framework based on nothing else than relativity, the laws of physics that we know, including something that we don't know what is, but it behaves like matter, fulfills every single observation that I know of to a very good degree of approximation. What I'm saying is that if a framework which is based on general relativity and the laws of physics as I know them. If I take a similar framework, so what I'm trying to do tomorrow is that whatever the nature of this stuff is, okay, I put it in the cosmological context. I don't know what it is. I'm just saying it's a framework. It's just a strange particle or an object that evades microlensing for some reason. I can form galaxies and clusters and things as I see them. Now, I do the same conceptual thing with modified gravity. These I can state it with a high degree of confidence. Mark my words, if I put a framework for the dark matter, it will give me almost naturally, if I solve all the equations, the clusters, the galaxies of different sizes. If I take a single framework without a specified Lagrangian, again, so I'm playing the same game, taking a particle, I don't really know what it is, I just know its phenomenological properties, I don't know its very nature, but if I propagate that framework, it works. I take something I don't know in modified gravity, meaning something that it solves one problem and I want to see if it solves all the other, without knowing the underlying nature. So without knowing the Lagrangian of that modified gravity, it cannot do it. So there is a conceptual, profound problem there. And it's not that I don't know the nature of the dark matter and I don't know the nature of the Lagrangian, I prefer the one or the other. It's that one framework solves the problems I see and the other doesn't. There are minor modifications to this statement, but if I manage to go through the second part of the second class, we will agree that the concerns on the dark matter scenario are much less, even without knowing exactly what it is.
It's a matter of Occam razor, but we can discuss that in more detail.
Yeah.
Just to remind that we have a full question sessions, so we can ask much more questions to Fabio, including the lensing ones and many others. Right, so I would like to stop now so that we go to the break and don't delay the rest. But you have lots of times to ask more questions.
Write down the questions now, okay? Write your questions, because otherwise they will evade your brain.
That's a good advice, yes, please. So I'm sure many of you have questions, so just write them down and we'll discuss them in the afternoon.